and at the middle you have the vessel itself. If we go down here, let's do this one. We have what is referred to the wave reactor. Okay, I want to believe. Are you able to see the laser pointer on the screen on the diagram, class?
Yes.
Great. What you have here is a wave reactor. What it does is that it provides a kind of gentle mixing. This is majorly used if you are cultivating cells, right? If you are growing mammalian cells, which they are not supposed to be exposed to high shear forces, unlike the one you have here at the top left of on your screen, which is a continuous state kind of reactor, which deals with bacteria and other cells that can withstand a level of shear stress. We'll come much more in detail to many of these devices. Please, again, feel free to interrupt if at some point you feel that you are not moving, maybe I'm too fast with the pace of explanation. I would gladly interrupt to provide more input to that aspect. Again, just to further put in perspective that we are dealing with a device that will have several, there could be very small or very large in sizes, right? Typically, when you have such kind of setup in industry, they have the same functionality like the one shown to you, which has a number of sensors and a number of actuators. Both are regulated or monitored and controlled by the central control unit. Let me repeat a little bit. They're going to have a number of sensors. Sensors sense, okay? Sensors monitor the condition of growth. When I'm talking about sensor, I'm referring to the pH sensor, temperature sensor, sensor components such as the foam sensors, dissolved oxygen sensors, and so on and so forth. The other part, actuators act. That is, actuator carry out a kind of action on the reactor. You have, for example, the motor that will rotate to mix the content is an actuator. The valves that open to allow a given feed or nutrient to go into the reactor, these are actuators. That is, it has a number of sensors that will sense the environment and the actuators that will act. Okay. Yeah, just to let you have an idea of, they could have different sizes. Let me give you much more a better approach, just to give you a little bit. I'll come back to this a little bit. If you look a little bit here, they said between 1 and 20 liters, they may be used for enzymes production or substance for molecular biology. And you have those between 40 and 80,000 liters. Okay, this is quite a huge volume, 80,000 liters, and they are used for antibiotics production already. You also have another version that could be between 100 and 150,000 liters that involve in the penicillin productions, amylase, and other amino acid productions. And the other extreme end, you have vessel size of approximately 500,000 liters, like those used in the beer industry for wine productions or beer productions, as well as some amino acid. Okay, this table just gives you a rough idea on how there's no unique size of when it comes to bioreactor. You will have different sizes, and that will depend on what is the target product. Okay, the target product will dictate. And again, at what industrial scale do you want to produce? That will also dictate. For example, in your house, if you decide to fabricate a small reactor for your beer production, for example, you don't necessarily need to go at this very large scale, because maybe you are producing for maybe personal or family consumption or friends consumption. You could limit yourself at something of 100 liters productions that is acceptable. Now, basically, in addition to looking at the product, that also depends on the scale at which you're operating. Okay, let me quickly pick a question here at the chat. The question is, well, not really a question, but the person wanted the lecture to be recorded. Okay, that's fine. Okay, let's look at much more again at what okay, now let's look at, by definition, what is a reactor. They said reactor provides an optimally controlled and homogeneous environment. I would like you to write down again two terms here: optimally controlled and homogeneous environment. Now, by contrast to the natural environment where cells find themselves, you realize that the natural environment is not controlled, right? If you take, if you look a little bit, maybe a sample of microbes, maybe growing on the maybe the leftover piece of meal that you abandoned, microbes are growing there, but they are not. The environment is not controlled. Okay, you agree with me? The temperature is fluctuating in the environment, and in the previous class, we learned that temperature fluctuation will affect the cell. Okay. Again, if you take a piece of meal that you have abandoned, microbes are growing. The environment is not homogeneous. In some part of that leftover material, you may have more water. Whereas the other aspect, it becomes maybe much more a solid form. One area of the nutrient may have more sugar. The other area may be perhaps having something else. Now, the bottom line is the natural environment is not controlled. The natural environment is not homogeneous. And what the bioreactor provides is solve those two problems. It provides a control and homogeneous environment that will make the fermentation proceed optimally. What do you mean optimally? So the cell could produce the desired product in maximum amount, so the cell could grow in a maximum growth at the maximum growth rate. That's why we said the reactor provides a control and homogeneous environment. Now, if I ask you to write about the reactor, I want to see the control and the homogeneous. I would like to expand on those two terms. Okay, I would like you to reflect, understand why you said that it's optimally controlled and why we're looking at an environment that's homogeneous. Now, just before that, again, if you have a question, please just unmute yourself, right? Don't be shy, just
can you please, yes, may you please re-explain about the optimal, controlled, and homogeneous environment?
Okay, thank you, Nanzipa. I'll go to it again to Nanzipa on this slide.
Thank you.
Yeah, the reason I said the optimally controlled is that you know that several parameters affect the process. You have the pH, you have the temperature, you have the dissolved oxygen, you have the dissolved carbon dioxide, you have the feed concentrations. All these parameters affect the metabolic activities of the cells. Now, if those parameters are not maintained at a constant value, which I refer to as set point, if you don't maintain them at a constant value, the fact that they are changing will make the cell to be stressed. For example, temperature could change and become so high that cell will die. That's why it needs to be controlled at the value or at set point value that makes the cell to grow optimally without dying. The same thing applies to all other parameters that affect the cell. By controlling, we mean that we want to maintain those parameters at optimum value, optimum set point value for the microbes to grow and produce the desired product. Okay, that's why we said optimally controlled environment. Secondly, we said homogeneous environment. Homogeneous environment, on the other hand, implies that the same amount of everything is found in different locations in the reactor. Okay, take a case of let's say 100 liters drum, right? Reactor, but let's just say something of 100 liters drum to be used as a reactor. At every point within that vessel, you have to have the same amount of everything available. What I mean is, you don't want to have too much sugar at the top of the drum and have maybe zero amount of sugar at the bottom of the drum. It has to be uniform. It has to be homogeneous. We don't want to have too many cells accumulated maybe in one side of the drum, whereas the other side has nutrient without cell. We don't want to have too much oxygen found towards those cells at the bottom of the drum, whereas the upper part, you have more of an anaerobic environment. You want to have the same of everything in all parts of your content of the reactor. Does that make some sense, Nandipa?
Yes, thank you so much.
Yeah, you see, you want homogeneous means you have to have the same everything and all aspects. And that you're going to realize that this homogeneous environment will going to become a challenge as we proceed further, right? When the scales increase, when you go to very large scale, sometimes it becomes difficult to have this homogeneous environment. But we need to achieve it. Always take entire class. I would like you to write this down. Microbial cells are very sensitive to the growth environment. Okay? Microbial cells are very sensitive to the growth environment. Now, what I mean by being sensitive to growth environment implies that if in the same reactor, you have some cells that are subjected to high temperature in some area of the reactor, whereas there's substantial difference in temperature in that part of the reactor, that will affect the cells. Okay, that will affect the cells. They could stop producing the product, they could actually die, or they could produce a different product. Remember what I told you, that it is possible to manipulate the growth environment and force the cell to produce a different product. It is possible to manipulate the growth environment and force the cell to produce different amount of the same product or produce different product, the same cell. Now, there's another new word I would like to reflect your definition of reactor: containment system. Now, what do you mean by containment system? We have three words here: optimally controlled, homogeneous environment, and containment system. I will allocate you 1 mark if you give me, sorry, I'll get 0.5 mark. Okay, I'll give you 0.5 mark if you're able to tell me what I mean by containment system. You can just unmute yourself. What do we mean by containment system?
Can I? Oh, okay.
Okay, go ahead.
By a containment system, it's a system that doesn't allow contamination. It doesn't allow. Sorry, Prof.
Yeah, it's fine. It's fine. Again, the class will assist in adding the 0.5 mark to your mark account. Okay, the class will assist in keeping that one in your mark account. You can contact her after the lecture so that she doesn't lose track of the explanation herself. Now, containment system basically implies that microbes must not that unwanted microbes must not come into the system, and listen everybody, and within the system must not find their way out of the system. That is, they have to be contained in that vessel. That's what referred to containment system, right? Microbes must not, contaminant must not come into the system. That's the first point. Secondly, those microbes you are growing must not find their way out of the system without your action. Now, here comes something to consider. When you carry out fermentation process, you have to ensure that even after collecting your product, you don't release the microbes, which are the microfactory, you don't release them into the environment, right? You have to make sure, especially if you are dealing with genetically modified cells, You don't release them in the environment, but your effluent need to be treated. You have to kill those microbes if it need be. You don't just release them into the environment, right? That is, containment implies that microbes do not come in and they do not go out, except the one you are dealing with. Now, 3 terms are on your table: optimally controlled, homogeneous environment, a containment system. Okay, that will guide your design of the reactor, or that will guide your understanding of what the reactor is about. Sorry, by the way, here I refer to the bioreactor, biological reactors, which are different from other reactors. You have nuclear reactors and other shape of other reactor terms, but here we're dealing with a biological reactor or bioreactor, not nuclear reactors or other such form of reactors. Now, okay, we have already explained homogeneous control environment. Homogeneous means the same throughout. Control environment, we said, maintaining all the conditions at optimum set point. Now, this slide says there's no universal reactor. That is, they could have different shape, different structure, but there are a couple of things that they need to meet, a couple of requirements to be characterized as a reactor. That is, a couple of features that are common to all reactors. That's what I want to pass across. You have some features that are found among all forms of reactors. Let me just pick. I don't seem to. Blah blah. We want these marks. Okay, all right. I thought it was a question. Yeah. Of course, bonus marking will be given to people if you actively participate in the class, and to participate actively implies that you have to engage with the resources in your model environment so as to understand and follow when explanation goes on. Class, let me give you a hint how to further enhance your understanding in this module. Each time that we have online lecture or even face-to-face lecture, since you already have all the resources on model environment, I would like you to engage with those resources before coming to the class. If you engage with those resources, you're going to realize that you're going to have a very huge leverage understanding the explanation. First, engage with resources. When you come to the class, when the lecturer is explaining, it's much more easier for you to follow, and you will actually ask many questions as well. Okay, great. Let's look at some of the requirements of the reactor. Okay, these are a couple of the requirements. First, they said it has to be able to be kept sterile and withstand repeated cycle of sterilization at high temperature. Now, think a little bit. If you use, for example, maybe a plastic material or any other material that loses strength at high temperature, of course, your reactor needs to be sterilized, sometime at 121 degrees. If the material you use cannot withstand several cycles of sterilization at high temperature, that would not give you a very good reactor, okay? The second point is that it has to be able to carry out mixing.
Sorry, Prof, can you please go again to
okay. The material to be used has to be a material that cannot be damaged if you subject it to high temperature, 120 degrees or 121 degrees repeatedly, right? And I've taken an example of, let's say, taking a plastic bottle or a plastic vessel or any other material that would be damaged if you subject it to high temperature. That will not be suitable for you to fabricate a good bioreactor. Now, we said that it has to be able to withstand, to carry out optimal mixing. That is, the entire system has to be able to carry out proper mixing. Now, when you say the uniform and low shear, because you don't want to damage the cell, you don't want the mixing system to kill the cell, right, to break the cell. Now, adequate mass and the oxygen transfer. You want to have the same amount of nutrients every part of the reactor. You want to have the same amount of oxygen in every part of the reactor. You don't want cells at the bottom to be starving because there's no nutrient, and cell maybe at the upper layer to be having too much concentration of nutrient. That is, everything has to be uniform in all parts of the reactor. Well, when we say absence of a heat and nutrient gradient is almost similar to the previous one. What do you refer to let me take the case of a heat gradient, for example. Heat gradient pool is a scenario in which what you provide when you are heating up the reactor, because in some system you need to provide a heat to the reactor. When you are heating up the reactor, close to the heating element, the temperature is high, but away from the heating element, there's there's decrease in temperature. That implies that the temperature is gradually reducing when you move away from the heat source. All right, that becomes what is referred to as a heat gradient. That is not good for the reactor. The temperature has to be uniform. Okay, what referred to as a nutrient gradient is the same scenario. Maybe you are carrying out a fed batch system, and close to the source of nutrient, maybe there's high concentration of nutrient, and away from the source of nutrient, there's starvation, right? That is, you don't have the same concentration of nutrient in all parts of the reactor, right? That's maybe that also can cause what is referred to nutrient gradients. Suspension of solid, again, further support the previous point. If there is uniformity, there'll be suspension of solid. The solid will not deposit at the bottom of the reactor. Take a little bit of your flask, for example, which you prepare a mineral salt solution to grow the microorganism, and the mineral salts are depositing at the bottom of the flask, right? That is, the solid part, undissolved components are getting deposited at the bottom, right? We don't need to have that kind of scenario in your reactor. Everything has to be uniform. Yeah, gentle heat transfer, that is well understood. That is, the heat, the temperature must not be higher in some locations. It has to move, it doesn't have to be too high, right? It has to be quite an acceptable temperature source to prevent cells from dying. Now, let me go to the H point: suitable sensors for process monitoring and adequate control mechanism. Now, your reactor has to have a number of sensors. Sensors, think of sensors like probes. Take a little bit the pH electrode you use to measure your pH. Okay, that's a sensor actually. When you talk about sensors, we're referring to devices that look like your pH probe, and you have similar device for virtually all parameters. Right? You're going to have a temperature probe. You're going to have, let me actually just show you one of those temperature probe. I don't know if you're able to see, this is actually a temperature probe, okay? This is one of the temperature probe I have on my desk here. What it does is that it captures the temperature in the reactor, okay? You're going to have sensors such as a temperature probe, pH probe, dissolved oxygen sensors, carbon dioxide sensors, different mineral salt sensors, nutrient sensors. All those sensors will capture information from the reactors. Then you need to have actuators. Actuators will act like the valves opening or closing. These are actuators. Like the motor mixing the entire system, these are actuators. Okay, that is, you have a combination of sensors, actuators that are found in your in the system. Okay, long-term stability, compatibility with upstream and downstream processes. Because we've already covered what are the upstream operations. Your reactor has to be able to accommodate all the upstream operations and downstream operation as well. Okay. More importantly is ease of sterilization. That is, the device has to be able to be sterilized. Now, that comes a little bit when you are dealing with reactor, maybe a small size reactor, let's say 1 liter, 2 liter, 3 liter, you can easily autoclave the entire reactor. That's sterilization. Okay. Remember the heat sterilization that will carry out in micro360. When you have a small size reactor, 1, 2, maybe 10, you can actually put everything inside the autoclave and heat it up. That's the heat sterilization. Now, what the size is a little of that, obviously, you will not be able to put it inside the autoclave, but to carry out in situ sterilization. Little bit what you saw in your prac, yeah. Class, are we on the same page? Is there anyone that needs more explanation on this slide?
Yes.
Okay, which aspect? Okay, what we have here are the features, the requirement that the reactor must have. Okay, and some point which I would like you to summarize on the slide is some key points that we need I need to mention here is point B, C, D, E can be grouped under the same point, homogeneity, homogeneous environment, right? Point B, C, D, and E can be grouped under the same umbrella, homogeneity or homogeneous environment. And these points are linked, I repeat, B, C, D, E are linked with ability of mixing the entire content of the reactor. Why I say so, if you have proper mixing, if the mixing is adequate, there'll be suitable heat and mass transfer. There will be avoidance of heat and nutrient gradient. If the mixing is, there'll be no suspension of solid, right? If you succeed and achieve proper mixing, it will take care of a number of points here. Now, the reason why I say so is, of course, you may be tempted of thinking that why can't you just mix at high speed? No. When you subject the system to high mixing speed, that could damage the cell, especially if you are dealing with filamentous type of cells. That could damage the cells. That is, here you are struggling to achieve mass and oxygen transfer. You are trying to avoid heat and nutrient gradients. You want to achieve suspension of solid, but at the same time, you don't want to kill the cell by mixing at a very high speed. Can you begin to sense a problem here, a challenge? You need to mix at a speed adequate to achieve homogeneity. At the same time, you don't want to damage the cell. That is, you have to carry out proper mixing at optimum speed to avoid killing the cells and also to achieve all the points listed here. Another key point here is sterilization on this slide. The reactor has to be able to withstand sterilization. That cannot be compromised, okay? You can't compromise the issue of sterilization. You can't compromise on that because you have to sterilize the reactor all the time. Okay, we've covered this slide already. We're going to look a little bit at some of the reactor use, okay? I would take, these are the complete list of the reactor, but just to give you a glimpse of some type of reactor available. I repeat, what you have here just a snapshot on some, not all, the reactors that are available. You have the stir tank reactor, which refer to the what I've been discussing a little bit earlier on here, which they have impellers for mixing. And you have the bubble columns reactors, which air, they don't have impellers, but air itself is used for mixing. Then you have the airlift reactors, but they also use air for mixing, but different configuration. You have the fluidized bed reactor. The fluidized bed reactor have cells that are attached to solid particles. That is, the cells are not in suspension, but think a little bit of bead, tiny bead carrying the cells. A tiny bead could carry a large population of cells, and you have several of such beads in the environment. You have the packed bed reactors. They also have cells contained in the bead, But unlike the previous fluidized reactor, the packed bed, those beads do not move. They remain static in the entire container. Okay, let me repeat a little bit. Fluidized bed, you have the bead containing cells, several of such beads, but moving. Think a little bit like, what can I use to explain? Think a little bit of like maybe grains of rice in the pot of boiling water. Okay, that gives an idea of a fluidized reactor. In the boiling water pot, you have some grains of rice, and each grain of rice carries a large population of cells. That is, you have cells entrapped into those beads, to those grains. And everything is boiling, mixed, turning around inside the boiling pot of water. Okay, so that could be a little bit how the fluidized reactor looks like when it's operational. But the packed bed reactor, think of, again, those grains of rice carrying in which cells are embedded, but they are maintained fixed in the container. In other words, they're not following the phenomenon of boiling water, right? When I say boiling water, that's just an illustration, because obviously you're not going to carry out the process at 100 degrees. Class, if you go and write in definitions that fluidized reactor have cells in the boiling water, I'll give you -1. Okay, I'm just giving a kind of explanation to ease your understanding. I'm not saying that cells are growing in boiling water. All right. You have the flocculator reactors, which is majorly used in the wastewater treatment plant. Here again, you have cells that are made to flocculate to carry out the removal. I'm going to come in details again to these reactors as lecture proceed. Now let's have a look at this diagram. Now you have it in your reading material. I will explain, and again, when you read this page, I would like you to explain it to yourself. Naturally, I would love to give to you as assignment, but I don't want to give much assignment, but I'd like you to explain the diagram to yourself. But I first give you a glimpse of the explanation to guide, to ease your thinking. Let's have a look at the different parts of these machines, okay? Again, entire class, please pay attention, all right? Pay attention, interrupt if you're unable to follow my explanation. Let's look at this central reactor that is here. You see the arrow going up is a pipe through which a number of gases can go out. You have maybe the carbon dioxide going out from the reactor or the oxygen going out of the reactor. That's an exhaust gas stream. Now, you don't have here a motor. Think of the normal motor that goes into the reactor. This is referred to the agitation shaft. This central shaft carries impellers or blade that are going to mix the reactor. They're going to mix the content of the reactor. Okay, that is, you have a motor here with a long shaft that carries the impellers. The impellers are used for mixing the content. Okay. We may have several layers of impellers depending on the configuration of a reactor. Now, the side of this reactor has a number of sensors. You have, for example, foam sensors. You have the first sensor that detects if there's foam formation in the process. Of course, as lecture proceeds, as we proceed in this area, we're going to realize that processes carry out sometime there's foam formation, and foam formation is unneeded, is unwanted, right? Is something negative for the fermentation process. A sensor has to detect if there's a foam formation so that proper action can be taken, right? You have the pressure sensors, that is, it detects the amount of pressures in these vessels. You have oxygen sensors, somewhere here, that is, it tries to find out what is the dissolved oxygen concentration in this machine. You have pH sensors that find out what is the pH of the entire broth, the pH of the entire culture medium. Then you have the temperature sensors. You have the temperature sensors that detect what is the temperature level within this device. Of course, we're going to have a pot a place you can take sample to go and carry out some analysis. Right, that's where you have a port here to take some analysis. Now, right at the bottom, we also have product recovery port. That is, at the end of the process, for example, you may decide to open this valve to harvest the entire broth that will now undergo the downstream operations. Now, looking at other configurations towards the left part of the device, remember, I told you in the previous class that pH is maintained by allowing an amount of acid or base to go into the reactor, okay? In this very case, you have only the acid container that is here, that this device will allow acid to go in, but very often also going to have an alkaline solution here that can also go to the reactor depending on the pH sensed by this pH machine, by this pH sensors. Now you have an anti-foam. Obviously, if these sensors here, the foam sensor detect that there's a foam formation, a small amount of anti-foam will be released, go to the reactor in order to prevent foam formation. In this reactor, again, you have another tank here that is feeding the reactor. That is, this tank contains the nutrients. It could be a scenario in which fed batch system is being carried out here. The nutrients are fed into the reactor, to this central, into this reactor. Something I'd like to pay attention is, let me go to this air compressor. Of course, I told you previously that in our processes, you have to supply oxygen. The air compressor provides oxygen, but keep in mind, the oxygen itself needs to be filtered. I repeat, the air provided need to pass through a filtering membrane, filtering compartment before going into the reactor. The idea is that all the microbes in the air will be removed here before the air goes into the reactor. Now, this unit where you have the dot, have a look at it, is referred to as the Sparger, S-P-A-R-G-E-R. Okay, the Sparger is the device through which air or air bubbles are liberated are provided into the reactor. Okay, what you have here is a Sparger, it's all written, but you're going to discover when you go much more in detail. You have a Sparger that provides air bubbles, that is, the air from compressor is sterilized here and discharged via the Spargers below the impellers. Class, something that you need to note at this point, which is extremely important. You see that the air bubbles are discharged below the impellers. I repeat, I'm going to ask the exam question. The exam class, air is discharged below the impellers, not above the impellers. Always, it has to be below, not above. I'm going to give you one mark to tell me why. Class, why is the air discharged below the impellers, above the impellers? Come again, Taye. Okay, that's great. Yeah, that's fine. Taye, you're correct. The idea here is that these blades would be able to break the bubbles of oxygen and enhance oxygen transfer, right? Enhance oxygen transfer. Remember the requirement of the reactor, there has to be suitable oxygen transfer. That is, dissolved oxygen is properly enhance the concentration of dissolved oxygen, because these impellers need to break the bubbles of the air generated, provided by the Sparger. That's why you place it below the impellers. Now, okay, something which I almost forgot here. Let's have a look at this stream a little bit here. Let me take from here. You have the slant here that went through the flask culture, eventually through the seed reactor, inoculum development reactor, which is served as a as a source which generates biomass to be inoculate this reactor. If you look at it, we have a smaller reactor here first, which was to build the biomass, and eventually the entire biomass is used as a source of inoculum to initiate this big reactor. This slide is very important. I would like you to spend maybe at the end of later in the day, we'll spend maybe 20 minutes or 30 minutes reflecting on this entire slide. Really, I really request the entire class, everybody, to spend 30 minutes later in the day when you finish the lecture, when you have rested enough, go through the entire slide, explain to yourself the different component of this entire system. That is, write it down in your own words. I repeat, invest 30 minutes today, going through the entire setup on this slide, write each component down in your own words. Explain what it does, basically. Explain what is the need of each of these this structure. Now, further details, again, here you have almost the same configuration. You have gas exhaust valve. You have a spagger bringing in sterile air, and again, the spagger discharges below the impellers. You have the agitating shaft that carries different blade. Again, I'm not saying that you just have to have 3 units of blade. No, you may have one or several, depends on the configuration of the reactor. Then you have the temperature probe again. You have the nutrient port here, the valve through which nutrient can be passed into the reactor. Now, this reactor has something new that wasn't introduced in the previous ones. What you have here is that a jacket through which cooling or hot solutions can be used to adjust the temperature of this device. Now, keep in mind that this jacket doesn't have direct contact with the culture. In other words, if you are passing a hot or cool solution here to adjust temperature, it does not directly impact the culture. To avoid contamination, it touches only the surface of the vessels to achieve the purpose which you want to carry out, but doesn't have direct contact with the broad environment. Now, further, it's almost the same scenario here, which you're going to have the mixing shaft, you're going to have the jacket. Well, in some reactor, you may not have the jacket, but may have other methods to control temperature. You're going to look at for example, the heating or cooling finger, right? You have the heating part. All these are other methods to adjust temperature. The same configurations, the same components reflect on this other system. I was on the same page. Any question, class, before? I was on the same page.
Yes.
Yes, I want to ask a question. Sorry, sir.
Yeah, go ahead. What's the question?
Yes, I want to ask a question based on the first diagram.
Yeah.
Yes, this one. Yes, I want to know what are these raw materials on the top left corner? Is it some nutrients, and what is happening at continuous sterilization?
Yeah, basically what you have there, you have the raw material referred to the nutrients. That is the medium that you have formulated to support the microbial growth. It has to be, you have to mix it, and it undergoes sterilization, continuous sterilization before it goes to the reactor, right? If you look at it, the same medium that has been sterilized goes to the inoculum inoculum preparation here, and part of the sterilized system goes into to feed the bigger reactor. That is, you have another tank here in which the nutrient is formulated, properly mixed, they undergo sterilization. After sterilization, it's moved into it feeds the inoculum reactors as well as the production reactor. Okay, inoculum is sterilized to feed all the reactors in the inoculum development chain, and part of the formulated and sterilized medium goes into the reactor. Now, if you refer to your, if you refer to the, just a minute, if you refer to the class track, you realize that the nutrient was just the nutrient was not sterilized separately, but the contrary, they put an unsterilized nutrient in the reactor, but sterilize the reactor and the nutrient at the same time. That's also possible. Okay, go ahead with your question, please.
I'm not sure whether I misheard you, but did you say that the inoculum is sterilized?
No. Please, thank you very much for raising that. Never sterilize the inoculum, please. Never sterilize. What I'm saying was that the medium formulated is used to feed the small reactor that grow the inoculum. Look at the inoculum line from the vial to the flask into the reactor. Inoculum must never be sterilized. Please write it down. Everybody write it down. Write it down for the second time. And I can assure you that after your first test, at least one student will going to write inoculum must be sterilized. This has happened over more than every year that I said to students, don't ever write this. At least one out of the entire class is going to write inoculum should be sterilized. Inoculum must never be sterilized.
Sorry, Prof.
Inoculum must never be sterilized. But I'm going to tell you something a little bit here. Class, are we still together?
Yes.
I'll tell you something here. This is a very real case of the process, but I'm going to tell you what happened. Listen and don't mix it with what keep in mind inoculum must never be sterilized, but there's one extreme case which I'm going to explain to you, and it's not actually sterilization. During the production of biohydrogen, class, I'm very specific here to avoid confusion. During the production of biohydrogen is a biofuel that some group of microorganisms can metabolize, can grow nutrients and produce a gas, which is hydrogen. Now, during the production of biohydrogen, the inoculum, the source of inoculum sometimes is heated up. Okay? Sometimes they will heat it up, sometimes even to 100 degrees. The purpose of doing that is not to sterilize the inoculum. The purpose why they are heating up the source of inoculum to 100 degrees is to remove other microorganisms that are not involved in the production of hydrogen. Because Clostridium that's involved in the production of hydrogen can form spores that will withstand 100 degrees. By heating the source of inoculum, you remove the methanogens and other organisms that may be available, with the knowledge that the main organism that you want to produce hydrogen will survive that temperature. That cannot be considered as inoculum sterilization. I think I'm clear enough, class?
Yes.
If you are reading some documents and you realize that they are heating the inoculum, that is not sterilization. They want to remove some unwanted microorganisms from the inoculum. They are very sure that the core organism, the key microorganism that they want to produce a product is going to survive that treatment. Thank you. And please never sterilize the inoculum.
Oh, sorry, sir.
Yeah.
Yes. Since we started learning about these bioreactors, we've been talking only about bacteria. So can we consider a process where we grow algae to produce something as fermentation.
Sorry, are you okay? Refer to microalgae, right?
Yes, sir.
Yeah. Okay. Again, yeah. You have approximately you have at least 2 types of reactors that are involved. They're also bioreactors. Okay, we're going to see those when you have 2 types. You have the photoreactor. The photoreactor will look a little bit like the continuous tear-down reactor, but you're going to have the source of light. Then you have the raceway pump, which is also a reactor, right? You have the raceway pump, which is a different type of reactor. Those 2 reactors are used by microalgae. That is, they're also referred to as bioreactors. Does that answer your question?
Yes, but I'm not sure if we can consider that as fermentation. Is it?
Okay. For example, let me just put it through. In the case of photobioreactors, you actually have I'm going to show you a little bit. Okay, I'm going to scan to another slide quickly to show you a little bit the photoreactors. Then we'll come back to the where we are. Okay, here you have the, okay, sorry. Here you have, these are the raceway pumps. Of course, you have the paddle for mixing, right? You have the paddle system for mixing. And again, you may have a number of sensors here, maybe to monitor the pH of the medium, to monitor the dissolved oxygen of the medium. But however, these systems sometimes do not have the strict containment measure. Right? They don't have the strict containment measure, especially the raceway pumps for microalgae. And again, you have the tubular photoreactors here. Sorry, just for your information again, you have the mixing here, which is equivalent to the mixing in the continuous tear-down reactor. Here you have the tubular reactor, in which the entire solution goes through the different pipe, transparent, I emphasize, so that they can be exposed to the sunlight. The sunlight will enable the microalgae to grow. Okay, and again here, at some point, there's always a tank, a reservoir, through which the conditions are monitored in terms of temperature, pH, nutrient, and so on. Okay, the entire system still goes through the different pipes and go down to a reservoir for the condition to be monitored. That is, just to summarize my answer to your questions, yes, there's a level of instrumentations, but that may differ from other common type of reactors.
Okay, thank you, sir.
Is it time already? Let's see how much time we've spent. 1 hour already. Okay, what I'm going to do is I will stop here for today. Tomorrow we're going to start with going much more in detail with continuous tear-down reactor. Okay, we're going to go much more in detail continuous tear-down reactor, looking at different parts of one of the common reactor. This one is actually what's referred to as the continuous tear-down reactor. Okay, this one referred to as continuous tear-down reactor. We're going to spend a couple of time on this very unit, and tomorrow we'll go much more in detail to different part of this reactor. So we have tomorrow is Friday, we have 7:45 lecture. Okay, there's the 7:45 lecture will take place tomorrow. And we're going to use the same Zoom link for tomorrow's lecture. Any question before I will close today's session?
Yes, Prof.
No, the micro304 pracs, again, is going to be a virtual prac, will be online. Okay. Any other question?
Prof,
yeah, go ahead.
Can I ask the mark allocations for the assignments that is due on Monday?
The mark allocation.
Yes.
I want to understand that, you're referring to what the discussions on the parameters that affect the fermentation process, right? Am I right?
Yes.
May I request that you first focus on getting it right?
Okay.
I understand. Are we much more comfortable seeing you being one of the best biotechnologists in the area of microbial processing? Even if you don't have the certificate, but if you're the best person in the world, I'll be so proud of you. Focus less on mark, but more importantly, on the knowledge. I would like you to be one of the leading person. What's the name? What's your name, please? What's your name?
Ziza.
This, I would like you to be the next couple of years. I would like you to drive a whole fermentation plant in South Africa. Do you have that deal? If you agree on that deal, I'm going to give you 10 marks. You have the deal
yes.
that the next
Yes,
10 years you will be driving. I will see you maybe producing lysine or any other product that is required in the South African market. Having a team of people working under you, or perhaps you driving operations in the whole plant in that area. I'll be so proud of you, right? I promise you, when there's a proof that you are driving that industry, I'll come there and provide and give you the 10 marks there.
How?
All right, okay. Have a beautiful. Any other question? Lugabalo, listen to you.
Oh yes, Prof. I needed clarification on the bioreactor diagram.
Which of the reactor, Lugabalo? Which one?
First one.
Pardon?
The first one.
Yeah, the clarification on the first reactor.
Yes, I need a clarification on the starter culture, the agar medium, and the raw materials.
The agar medium.
Yes, and the raw materials.
Well, you refer to the diagram given to you.
Yes.
I would like you to reflect on that diagram. Yeah, spend some time, reflect on it. You're going to find all the explanations. Spend some time, reflect on that diagram. But basically, the raw material is, you're going to have a medium that will provide a source of nitrogen, the source of carbon, the source of some amino acids needed, sometimes vitamins, mineral salt. Is the entire composition that will have to undergo sterilization. And you need to have those ingredients in the right proportion. Okay, that is, especially for industrial processes, large scale, the natural may not go for pure glucose, but they may go for some waste like sugarcane molasses. But that does not exclude the fact that they need to provide an additional source of nitrogen, vitamins, and other ingredients. Okay, it's the entire mixture of your carbon source, which could be sugarcane molasses, that could be other starchy material. Then your nitrogen source, that could be corn glycol, that could be yeast extract, the different mineral salts that are required for growth that need to be mixed in that first tank in the right proportion before it undergoes sterilization. Okay, this is basically what takes place there. Mixing the right proportion of each ingredient, subjecting it to sterilization.
Thank you, Prof.
Yeah. Okay. All right. Thank you for today. We're gonna meet again tomorrow 7:45. Okay, now ladies are asking for the assignment. You're going to have the list of parameters. No, take each parameters, not a separate list for those parameters affecting the growth and those affecting the product separation, because almost the same parameter affect, but a different value. Okay, if you take temperatures, just describe how it affect both pH. Sorry, how it affect both product formation and cell growth. Don't need to separate that. All right. Have a beautiful day, and we'll meet again tomorrow.